Our next speaker is Adam Dziedzic. Adam did his master's at the Warsaw University of Technology. Then he studied in many places in Denmark, at the Technical University of Denmark, at EPFL, and he did his PhD at the University of Chicago. He also worked in several companies and institutes like CERN, Berkeley's Investment Bank, Microsoft Research, and Google. And now he will tell us about the data provenance for generative artificial intelligence.
Thanks for the introduction. It's very kind. Hello, everyone. Today I will talk to you about how we can really trace what it actually goes to models that generate data and also what it actually comes from these models. So, first of all, probably most of you know that currently these models generate high-quality text. But not only text, actually, but they can also even write proofs. And these are very complex, actually, things that even we sometimes don't have even insights how to solve. Apart from text, they also can generate high-quality images. So these are usually pluralistic, and they closely follow exact prompts that we give to these models. And then collecting these advancements, we also have models from Suno that can generate music that adheres exactly to our needs. So these actually developments, they change the way how we really write, what we see, and what we listen to. Now, what is the source of the power of these models? These models are trained on enormous amount of data that comes in different forms. So, for example, many of these models are trained on text, such as news articles. Additionally, even the whole books, pieces of art, and also music. Now, what's really problematic is that this fact that we have this new model trained on lots of data and generates high-quality data forms so-called data loops. So we actually found recently, as discussed, that models memorize individual samples through training. So here actually is another aspect that I will explain very soon, how models who generate images in a progressive manner, so token by token, also memorize exactly the training samples. Not only individual images, but even the whole books. So very recently it was shown that models such as Llama 3.1 memorizes the whole book word by word. Now, so all of these different sources of data go to these models, and I would say it's problematic. Why? Because actually data is copyrighted. So we didn't have this intention to use such data to train these models. And probably most of you heard about many of these court cases, and there are currently, as of now, 25 ongoing lawsuits, and probably one of the most famous one is OpenAI versus the New York Times. So what are these really data loops? So we observed that we can generate enormously large amount of data of high quality. Therefore, this data is put on the internet and then scraped to train new models by the model providers. However, it was shown that if you train your new models on the outputs, then the models to be trained, they actually have lower performance. So one of our goals is really to detect that really is outputs from the models and goes into the training, so that actually we can ensure high quality of these new models. So it's even more, because currently the EU actually requires in the EU AI Act that actually these companies that produce data and train large amount of data, they actually report what data goes to the models and also what it actually is produced by these models. And actually this comes into effect 7th August next year, so very soon. So how can we really ensure that we can have provenance for our data? The main problem is that currently we don't know what is the training of these models. And as we just heard, we cannot really easily find what is really memorized by these models, and finally, also what is really what is generated. So how can we really address these problems? So first, I will present overall project that we are working on to provide provenance for data in generative AI. First part is memorization, so we just discussed about Francisca. So how can we detect what data is memorized by these models? Second aspect is to identify what data sets go into the model's training, and finally, then to also mark the outputs from the models. So I will go through that one by one, but before going into details, I have to give you also some background about these autoregressive generative models. So stay tuned, and you will just have a small intro into this. So probably most of you heard about this new paradigm of the next token prediction. So for example, here we give to the model the prefix G8N, and actually then the model generates the next token. In this case, we will have just an equation to show the factorized ability for the next token prediction. What is really advantage of the fact that we operate at the level of tokens and not, for example, individual pixels? So first of all, these actually models have amazing scaling laws. So it was shown that if you just train models with more data, with more compute, and these are bigger models, actually you improve their performance. Also, they were shown to have amazing zero generalization. So you don't even need a model for specific tasks, the model can perform very complex tasks. And now, how can we really go from this language domain prediction to the vision domain? So it was shown that we can do that in the vision domain for images. So we generate here the images kind of also by tokens step by step. In this case, updating the level of scales or resolutions. The resolution R1, so it's kind of like a vague idea on what should be the image. Naturally, then specify with every single next resolution more details about the given image. And finally, we arrive at the final R1 resolution that actually shows the final image with all the details. So how do we really train these models? So first we start from training this V2VAE, which is vector quantized vision encoder. So here basically we take the image, just of latent space, create the tokens from this latent space, then actually go back to the latent space, from tokens, and to the final image. So I'll show more how we do this quantization of the images to tokens. And once we have these tokens for the images, actually we can train the model to predict these tokens, meaning that you basically give to the image a couple of tokens, and then the model can generate the next token, so generate the whole image based on these tokens. So also I'll describe very soon briefly how we can train the transformer to actually predict the tokens. So first, let's start from how we can really quantize this image. So how do we go from the original image to the token space? So we have initial image here of the cat, and we just encode the image standard coordinate, and we have the latent space. Here in the latent space, we can actually quantize these representations to tokens. So how we're going to do that is that we have something which is called code, which is a dictionary, with each entry being 32 float values. We have, in this case, 4096 of them, and we express latent space via this combination of the entries with the code. So actually, this codebook is this quantized representation space. Once we have these tokens, then we go back to these values from the codebook, have the representation in the latent space, and then we decode that back to conv layers to the output image, which is in this case the initial. So here is how we can find the tokens for a given image, and now is the question how we can use this part transformer to predict the next token based on the previous ones. So it's relatively easy. Start from some start token S, give it to the transformer, and generates as the resolution. So here actually generate all the tokens for a resolution. And actually this RM1 is compared with the expected value, our ground truth that comes from this video. And we use standard percentage loss to just train the transformer to correctly predict the next resolution. Once we have the resolution 1, then we go to the next resolution. And then here we take the ground truth solution and we predict again all the tokens for the next resolution. So R2. And again we compare with the ground truth that we have from the DQBE, and we have loss to train the transformer to better predict these topics. Okay. Any questions regarding the background? Small intro in the background. Okay. questions. Okay. So let's
Let me actually one small
okay,
question.
go ahead.
So how does this compare, for example, to diffusion-based LLM or diffusion model? I mean, in the sense that the diffusion model basically puts a lot more space instructions and defines like step by step. And for example, we can also do LLM based on diffusion, which like improves the text, full text like one step, and doesn't this actually okay?
So actually, so you mentioned LLMs, right? To generate token by tokens. We mentioned at the very beginning, it's tokens G8 and Apple, right? So basically, different models were, as we said, generating. So as we said, it's kind of work with this high-dimensional space to find this noising of this image, right? Here it's that we just so basically LLMs have this sort of prediction. So basically, you have the text and you predict the next word, right? And then here the idea actually was to paradigm the images, the vision domain. Why? Because it just scales much better the vision models. And then it was shown that we can do that actually based on this next scale, next prediction. And this actually is a different approach how we can do images, and was shown that currently actually outperforms the vision models.
It is not quite similar to diffusion, so there's like gradually upscale. Okay, basically,
so basically you are saying that, this aspect that you, maybe this one. Okay. This one. So kind of the noising from initial stage. However, here actually it happens on the discrete space. So actually every single of these solutions actually is expressed by tokens. So don't predict the next you predict the next thing, but it's discrete. And then you go back to the latent space. Okay, great. So are there any other questions? If not, then we can go back to this framework. So we have to, so now actually let me dive into how we actually discover memorization, but this time in this regressive models. So here, what we really propose is that we put a method to extract which data points from training set of the given which model actually is memorized. So how do we do it? So we start from this initial image, we encode the image to the latent space, and we then quantize the image to get the tokens. In the standard way, as I showed when we train these models. Actually, then we feed these tokens to the var transformer, this model that generates the next tokens, then to predict the tokens. So basically, we have this ground truth and our prediction of tokens. And then actually, we compare this token to the ground truth, the upper part, and predicted ones. And we compare the distances to just have some estimation which of these images actually might have been memorized by the model. So we actually choose the images that actually have the smallest distances between tokens that are gone through and the predicted ones. So then once we identify some of these actually most memorized images, actually we take the prefix token. So imagine that you have this generation of the image, same as in the text that G8N say, okay, we say, okay, model says Apple, model generates Apple. Same here. We present to the model few first tokens for a given image. Let's say this first one, like R1 or 2. And actually then, what we show actually is that in many cases, these models can complete the whole image starting from the first few tokens. So actually this, after decoding, these images, they look exactly the same as this initial image. So this actually was a very powerful way how we can easily find memorized images in this image trace. And then we also had some quantification of distances. So how close are these initial training samples to the output samples, and they are usually almost identical. Now, how many of these we can discover to be memorized, these images? So we actually tested, in this case, 3 different models. So here we actually report how many of these memorized samples we were able to identify. So really, after a small amount of like a search, small search, we just discovered even hundreds of these images being memorized, which actually means that these models can generate amazingly high quality images, but at the same time, for some specific samples, they just exactly memorize the tokens that are for these samples to be generated. Now, you can also see qualitatively how it looks. We have the first row, upper one is an image, is for training, and on the bottom line, we have some images. So after our extraction, it's memorized samples. So really, these images are identical in many cases. Now, so once we know which parts are memorized, then we go further. Then we now discover what data sets were used to train this. So, you know what? Up to 2024, it was really the case that people wanted to do membership accounts. They wanted to really find out this answer to the question, membership accounts attack, what's data point used to train a given model. So this was standard question asked for many years in ML, and after 2024, actually, people believe that it's possible. However, what we showed is that if you just have some sort of data point, in this case, a piece of text, and you want to find out what's this text in the model's training set, really what you get actually is random guesses. You cannot really identify for the individual sample if it was not or used in the model's training set. And we have a bunch of results for that. So I showed that for both language domain and vision domain, this is the case. Function inference really does not work to identify individual samples in the model's training set. So what we actually propose is that we don't focus on individual samples. However, we can do now simplification to the data sets. So the question changes to what's my data set used to train a given model. So this actually works, for example, if you have a large portion of text, can be, let's say, your blog post, your papers, the whole books. And really what's important is that we have the critical number of samples to be able to identify if they together were in the most training set. So you have to identify really what are between the samples, some relationships to make this really pattern memorized by the model. So how we will do that is that we inspect how the model behaves on some suspect data versus some unseen, we call it handouts. And actually for these sets, we generate these scores. And actually based on the scores, we compare them. And then we have a verification if that actually data set was member or non-member. Actually, our method gives us also guarantees, based on, in this case, either p values or e values. We have some guarantee if the given data point, set actually was in the most training or not. And actually, this gives us a more powerful way, for example, for book writers or for blog writers, or even us as makers, to find out if they were used to train a given model. So now, what about data that goes out of this? So the outputs from models. How can we identify which of them actually were generated? So you already mentioned this aspect, this question regarding this generation. So generate these images scale by scale until we get to the final highly realistic image. Now, it's even actually more interesting is that we don't even generate these images token by token, but ultimately the current paradigm is to generate these images actually bit by bit. So imagine that for the given solution, actually you just generate from the model bits. And then it's also on the scale level. Solutions R1, R2, R3, and so on and so forth. So now the question is, okay, how can we really watermark? Meaning that how can we really change this generation to really label a given output? So what we actually found in our lab is that we can do that if we slightly influence this bit generation. So we call our method bitmark, which published this year. And then we slightly nudge the model to generate certain specific pattern of bits. So how it really happens is this. So we have this initial, in this case, 30-bit one, and then we define some form of sequence of bits that we want model to generate. So we have actually, in this case, simplified red list and green list. And red list is composed of two sequences, 0, 1, 1, 0, and green list 1, 1, 0, 0. So now, given this bit 1, do you have any guess what should be the next bit to complete the green list? Excellent. 1. Very good. Thank you for the contribution. So indeed, we want this model to generate the bit one so that we force, okay, actually encourage the model actually to generate more of these sequences from the green list. So how we do that is this. So we have here probability for the token being one, split being 1. So basically, this is the bit one. It's actually some output, some logics from the bit one and for the bit 0. And we also have adequately, respectively, probability for the generation of the bit 0, signed based on the logic, just takes up as logics. And now, how do we really nudge? So encourage the model to generate these bit 1 and not bit 0. So we add here this parameter delta that actually gives higher probability for generating bit 1. But the delta parameter allows you to also control how much you really influence the model, the generation of the model, and also how much you can really discover if this given data point was by us marked. So then once we influence this model to generate more of this green list sequences, how can we then discover if a given image was watermarked by our bitmark or not? So here we have a null hypothesis. So we actually assume that everything is benign. So every image actually was not marked by us. So the sequence of bits that we discover are roughly the same number of the green list sequences and the red list sequences. Now what actually we do is that we have some gamma t actually is expected number of the green list sequences, and then corresponding 1 minus gamma times t red list sequences. And c actually is the number count in this given image of the green list sequences. We just complete the z-score. And actually, if the z-score is above a certain threshold, for actually guarantee, then we have very high confidence that this actually image was watermarked. Okay, so overall, what we really want to achieve is to have this unified provenance framework to identify what data goes to the models.
Okay. I have a question about watermarking. So you have to assume that the adversary is somewhere there and he wants to remove the watermark, right? So, and the adversary should be aware of the watermarking algorithm that you have.
Yes.
So do you have kind of like any proof that secure against any kind of manipulation or like removal of watermark?
Yes. So yes. So what we really think here is this. So the watermark is inspired by this data loops. So we want to detect for a model provider if the given image is memorized or not. So imagine that you are OpenAI and you generate your images, and then you want to ensure that you don't train on these images.
Okay, so it's a different model. So basically, then you don't have like adversarial someone who would like to like change the watermark because okay, I see.
It's kind of matters for providers like OpenAI, Google.
But like so ideally, maybe these companies would like share between each other like their watermarking methods, and then like OpenAI would know, okay, this was watermarked by Google, something like this.
Yes. Currently, I think that the biggest issue is if you train your own data.
Okay.
So on their own, like
longer looks, right? So I trade on Google.
Yes.
Google.
Actually, so this is a very good point. It's actually watermark. It's radioactive.
Radioactive.
Yes. Which actually means that if you train a new model on this data, actually the model generates data actually is also watermark. But this is also a very important aspect of like the threat model, right? So in this case, so Google or OpenAI, they don't want to train on their own data, right? So even if somebody would remove this watermark, then they would potentially train on maybe a couple of samples that they start coming from them, right? So of course, we also tested this watermark, so it's robust to like many manipulations of the images. So we have here it's a guarantee, like the statistical guarantee, it's not a cryptographic guarantee. And the second part is that, of course, like we tested that to be robust against, for example, augmentations of the images, and that somebody might just slightly blur the image or compress the image. So despite that, it's still watermarked.
There is this literature on cryptographic watermarking. It's called pseudo-random codes. Maybe we can take it offline.
I think it's also a very hot topic, especially the language domain. What is the best way to watermark? And then I think that one of the major problems is not to give guarantees to the watermark exists, or also a problem with the forgery of the watermarks. So somebody might just take an image and try to recreate this watermark, the other image that should not. So in this case, coming from the AI. Okay, excellent question. So we can discuss more. So overall, what we want to actually find out is what data goes into the models, what data actually comes out of this models. So why does it really matter? Because ultimately, we really want to contribute to achievable and enforceable AI. So we want data to be protected in the EU. Currently, EU leads the leadership in the sort of AI, and really without the methods, it actually cannot be achieved. So we want to contribute to this aspect. Second thing is that we want to protect also our data, individuals, us, groups of organizations. And then also we would like to generate this data in a safe way, because then if we can generate this data for the political domain, other specific domains, we can also contribute to new developments. And finally, also we want to prevent misinformation. So we actually want to find out if the given sample is generated or naturally created. So overall, we want to identify this data ingested and generated by Gen AI. This can help us to break these data loops, that we don't have this degradation. And then finally, this will benefit society, our citizens, and also organizations to really have a safe data. And then this actually framework is still under development. And then there are many aspects you heard more about memorization, more efforts towards certification, and finally especially by Stefan, really make this watermarking also proven. Currently, it's statistical guarantees, but we also would like to go a bit further so that we can really have some proofs that can help us identify the. Now, I wouldn't finish here because what actually we are organizing this year and also next year is European Championship. What actually is that is we go across Europe to different cities to organize regional events. It's kind of like a hackathon for a set location.
And it's actually in 2026.
Yes. So actually,
you can
You haven't.
travel in time.
not yet. It's a good point. So actually, we have actually will be back in Warsaw next year, more than once. But next year we will be here for sure on May 9th and 10th. And actually, we organized this one of the rounds of the European Championship. And we would like all of you to participate in this event. So how it's organized is that we already went to Paris last weekend. We have first best teams from Paris. And then we also go to Vienna in December, go to Stockholm in February, to Barcelona in April, also probably to Munich in March, and we'll be in Warsaw in May. And after all of these regional rounds, actually, we'll have big grand finale for all Europe at CISPA, we're working. So the first three teams from this local championship from Warsaw will advance to this final at CISPA next year in May. Sorry, next year actually in July will be the final. So this okay, it's kind of like inside, like small like peek into how this really looks. So it's actually me and Francisca, we are here in Paris. So it's the same kind of type of slides. So we introduce here what actually participants will work on. So how it's organized is that you will have this kind of scoreboard, and then there are different teams here ordered by their scores. You have 3 different tasks for a given regional round. Actually, you have 3 tasks to solve. The teams are usually of 4 people, and then you compete against other teams for the given round to get to the one of the 3 places, and eventually to become European champion in AI. So this scan this code or visit this website, and you can register, and hopefully we can see each other again in May. Hopefully. So with that, I would like to finish, and then I can also give this overview of the main topics, and I'm happy to answer any further questions.
Do we have any questions to Adam?
Okay, so like my first question is about data training loops, because there are some use cases, models, for actually generating data for the model, even by the model itself, is actually very welcome. Like take alpha geometry, like define, or AlphaGo, which plays Go and beats human champions. Basically, there are some cases where, for example, we have a very discrete space, like axioms of geometry or the rules of playing Go, where actually synthetic data directly from the model itself is beneficial. So do we have a unified framework, a way of distinguishing in which use cases to actually want those data loops and in which we do not?
Yes, very good question. So in your scenario, this is very, I would say, controlled environment. We have specific data to generate to improve your next model. We actually went from Francisca to OpenAI this year in May. And actually, we also met with the CEO, Sam Altman, and for him, the biggest problem was that the data that actually now comes to their training is generated. And actually, they want to prevent it, they want to train additional data. So in this scenario, that they actually happen to be designed the watermark for, so you scrape this data from the internet, this control environment that you create better data for your next model. It's more like somebody generates data, don't know how is the quality and so on and so forth. And you don't really want to train on this data. It's artificial thing. So there are many problems with that. For example, if you now ask the model how does a small child of a peacock, it's like a beautiful kind of scaled down peacock. However, it's not like how a baby peacock looks like. So we want to prevent such model biases. So it was shown that basically what's happening is if you train on this data it's generated recursively. So the next generations, at some point model kind of collapses to like one mode. So model with more generations kind of cuts off the tapes, the distribution. So we want to really prevent such model bias.
Yes. So thank you very much for both talks. I'm from a slightly different domain, but I was able to follow presentations.
Great.
Thank you. So my question sounds a bit more general, but I was curious about this. So is let's say the fact that we look for no memorization, so does it imply, let's say, that we are looking for uniqueness? Let's say, it could be said that correlates with some uniqueness, for example, in images, right? Generation. And it was said that it doesn't impact on performance for vision, but how does it look for length? Because I can imagine that vision, for example, we want to generate a unique image, but how about text? Because when I saw the example of Apple Word, then the search for uniqueness, language generation, does it have an impact on performance?
Actually, it's a general phenomenon. So what's really happening is that memorization that we here talk about is so-called unintended, meaning that you memorize individual samples. So we don't want model to memorize individual samples. Like for example, users' phone numbers. In most cases, like I don't want my phone number to be on ChatGPT so that everybody can just find out easily, call me. So we want models to learn patterns. And basically, if so, a very interesting paper actually from Meta this year, they show that you can train the model on basically random strings, and the model tries to memorize the strings, right? But the whole model capacity goes into memorization of these strings, right? So we don't want that. What we really want, the model generalizes. The model learns these generic patterns that are usually useful, right? So what's happening is this, that when you train the model, at some point model goes to this mode that it really stops memorizing individual samples, sequences of text or tokens from because here is also the same thing, tokens from images, tokens for text, right? So language or vision, actually, in this case, they are unified. And then you want to really devote this model's capacity to memorize the individual, to memorize the general patterns that are reusable, and not to memorize these individual samples. So in these cases, like language, vision, video, music, all of that actually is unified. You have like, especially in this case for the progressive models. And there is one more thing. So we also found that for SSL models, statistical learning, is that you train on images themselves. Don't have or also text. Don't have any like supervision in terms of like labels, right? Actually, in this case, actually, you sometimes have to memorize some samples that are from distribution tail. Some sample is basically very rare, and then you don't have many samples to learn the pattern. So in this case, it's better if the model actually also can memorize this specific very rare sample, because if the new rare sample, like if somebody has a specific disease, comes, you at least know more or less how to react, how to really predict for these cases. In the more supervised manner, if you have mislabeled images or basically like some form of like misalignment between the caption of the image and the image itself, then memorized samples are in many cases just mislabeled, like wrong caption for a given image. So actually, then you want to remove such highly memorized samples because they are just not useful at all for that. And then removing these memorized samples actually can help to even increase model's performance.
Okay. And is there a hard limit this process? Let's say, because how does it scale memorization with the attention needs attention? Sense that if you want to look always for a new path, new trajectory, is it possible? Let's say to zero this
Utilization. So model has capacity. We estimated something like 3.6 bits parameter. And then what was shown is that if you train the huge model on a small amount of data, model will memorize everything. So you can just ask model any like few samples and any few tokens. Okay? So it's purely memorization. Now, if you train on bigger data that actually model can memorize, model starts really generalizing, starts like learning these general patterns that are reusable. So ultimately, if you train on unlimited data, models cannot memorize because they have to learn these patterns. So in the limit, you have unlimited data, yes.
Do we have any more questions? If not, then let's thank